Hello, my name is Alex Spaden. I'm an undergraduate at the University of Michigan studying nuclear engineering. Over the summer, I've been in the SURE program working with the Detection for Nuclear Nonproliferation group. More specifically, I've been with a team of people working on a dual particle imaging system. What it is a system that consists entirely of scintillators, which is a type of radiation detector that detects both photons and neutrons and uses them to map local sources in the environment. Scintillators work when a particle, such as a photon, enters the material inside the detector and either scatters or is absorbed. Both of these interactions causes the material to emit light. The amount of light that's emitted corresponds to a certain amount of energy deposited in the detector. This system could be useful for applications such as when you want to know if there's a source of radiation inside of a cargo container, or if really anything where you need to know where radiation is coming from. My contributions to this project have been in modeling the system and its response to various source arrangements using VisEd, short for Visual Editor, or MCMP. MCMP is a program that stands for Monte Carlo and Particle. What it is a program that simulates the transport of neutral particles, such as photons or neutrons, through user-specified environments. The user tells the program what it wants to be in these environments by using text-based input files.
Using VisEd, you can make 2D and 3D visualizations of the case that you're simulating using just the input file associated with a run. For example, this is a top-down view of the imaging system that clearly shows the two planes of the system. As you can see, this can be very useful in making sure that everything is in the right place before or after running simulations that can take a considerable amount of time to complete. VisEd can also produce 3D images such as this one that shows the arrangement of the scintillators in the planes. I'll use these 3D renderings to explain why detecting both photons and neutrons is important. Nuclear material undergoing fission will emit both these particles, and each can be stopped by different types of shielding. Neutrons are better stopped by materials made of lighter elements such as water or plastic. Photons, on the other hand, can be effectively stopped by heavier materials such as lead. If nuclear material is shielded by just one of these types of materials, the other particle will still penetrate through to the detector. In a realistic scenario, it is entirely possible that both types of materials will be present. Looking for both particles will still be advantageous, as any particle that escapes will still help paint the picture of where the source is. So how is this picture painted? To figure out where the source is, the imaging system needs to know both the energy deposited by a particle in the detector, and for neutrons, the time of flight between the two planes of scintillators. The equations shown then convert this data into an angle. This angle creates a cone of possible locations extending from the system. When these cones are back projected onto a sphere and added together after several are drawn, the resulting image will highlight likely locations for the source. This brings me to the cases that took the majority of my time over the summer, simulating the response of the system to mixed oxide or MOX fuel canisters. MOX fuel contains oxides of more than one fissile element, such as a combination of uranium and plutonium oxides. More specifically, the simulations tested how the system reacted to two of these canisters in varying angular separations relative to the imager. These measurements would demonstrate the ability of the device to tell between multiple sources in close proximity. This highlights one of the reasons MCMP simulations are done. These simulations allow for predictions of the capabilities of the system and also help prevent from performing measurements that won't produce meaningful results. Lastly, I'd like to thank everyone who helped me this summer, including Drs. Pozzi, Flaska, and Clark, and Alexis Pocherson Riviere, Michael Hamill, and Kyle Polak. Thanks for watching.